Great. Thank you for the introduction. So our group receives research support from GE Healthcare. And so there has been tremendous progress over the years in 3D dynamic MRI. When I started in grad school, I was working on 40-flow denoising. And this would be one of the data sets that I'll be processing. Now, last year, I graduated. And when I look at results produced by Joseph Chang, you can see there's tremendous improvement in both image quality, apparent resolution, and also SNR. And so this kind of improvement has many contributing factors. There's improvement in sampling, improvement in better spatial temporal model, and also more and more, as mentioned by the previous speaker, there's better binning and gating algorithms. But I also want to talk a little bit about the downside of doing these gating or binning. Now, inherently, when you do these types of technique, you're losing transient information. For example, in an example here in lung imaging, where if we reconstruct a low-resolution, high-frame-rate image navigator, from this, we can extract motion and then bin according to this motion and bin them into several frames and create these gated image reconstruction. But if you actually look at the image navigator, there are really tremendous amount of information that are actually not captured by the regular motion part. In particular, you can look at these motions. There's the patient coughing in the beginning, and then there's also irregular breathing pattern. And so whenever we do these gating or binning methods, we're intrinsically losing all these information. And some of them might be of interest, of clinical interest, and in applications like DCE, the transient information is particularly important. And so in this work, we're interested in reconstructing 3D dynamics from non-gated acquisitions. And so there are a wide range of related work, starting from real-time MRI to just regular DCE, speech MRI, and so on. But what's really different here is that we're interested in large scale. We're really interested in recovering the rich dynamic information, but at the same time, still having the adequate spatial resolution. Now, in particular, this is one of the results that we managed to reconstruct. This is a DCE scan. As you can see, we get both the respiratory motion and also the contrast dynamics. And I'd like to emphasize here is there's no binning going on. We're basically reconstruct whatever is happening during the scan and showing it right here. Now, there's a few challenges involved in reconstructing this image. In particular, if you're looking at the data sizes, we're basically asking for a 100 gigabyte image from 2 gigabyte of K-space. And so there's the challenge of undersampling. But even if we manage to deal with it, there's also memory costs and computation that we have to take care of. And so in this work, we propose two innovations to deal with these challenges. One is a compressed multi-scale lowering representation that allows us to constrain and compress the problem. Another innovation is a streaming or stochastic optimization reconstruction algorithm that allows us to process one frame at a time and drastically reduce the computation. But first, I just want to mention in the acquisition side, in order to make use of all the information we can get from the data set, we're using these two 3D continuous acquisitions that can efficiently traverse K-space. But even with these very efficient K-space trajectories, going from them to the image is still fundamentally underdetermined. But from compressed sensing, we know that where our K-space measurements are incoherent enough, and in addition, we have a compressed representation that can capture the dynamics, then there's still hope that we're able to recover the underlying image. And so in this work, we consider the matrix model, the multi-scale lowering matrix model. At a high level, this model represents the spatial temporal image as a sum of dynamics of multiple scales. And just pictorially, you can see that it extends both low rank, locally low rank, and low rank plus sparse. And so because of time, I won't be able to go into this model in detail. But the important point here is that using this model, we can then be able to represent this 100 gigabyte of image using only 1 gigabyte of the coefficients. And so putting this back to the compressed sensing framework, what this means is that in principle, we can recover the 100 gigabyte image from the 2 gigabyte K-space. That's in principle, but in practice, unless you have a very, very, very expensive machine, optimizing on a 100 gigabyte image is still very, very, very difficult. And so similar to the previous speaker, instead of optimizing for the image directly, we optimize for the representation. Now this allows us to bypass the difficulty of storing and processing the 100 gigabyte image and allows us to make the reconstruction feasible. Okay. So in particular, this is the objective function that we're considering. We're optimizing directly for the left and right singular vectors. This goes through the block reshape operator, sense operator, Fourier transform operator, and then meet with the K-space, and then perform the data consistency. Now this is in general known as the Beer-Montero heuristic, and one of the nice property of this is that if the rank that you prescribe is larger than the solution of the rank of the solution, then you can actually guarantee to converge to the global solution. And so in principle, we can solve this and recover the underlying representation. But still, there's the difficulty that we're optimizing over thousands of K-space timeframes and coils, and this means that if we do any kind of conventional iterative algorithms, this would still be prohibitively expensive. And so instead, we propose to do a streaming reconstruction, and the general idea is that we pick one K-space at a time, process only one time frame and one channel, and then from each of them, we can use it to update our underlying representation. And this is actually very similar to how machine learning you would do training, for example. Now, because our memory footprint is actually reduced to so much, we can actually use GPU to help us to accelerate the reconstruction even more. In particular, our reconstruction time goes down to about 1 minute per frame. And we're also using a Python toolbox that's to reconstruct this data set. So all of these together allows us to create data sets as shown here. Because it's 3D, we can also rotate it to different frames, and you can see the respiratory motion and contrast. One thing to note is that there's actually some bulk motion when the contrast is injected, as shown here, if you look at it again. And so all of these would not be possible to be seen if we do gated or binning reconstruction. Now, this patient doesn't have a lot of bulk motion, but here I'm showing another example where there's extreme shift when the contrast is injected. And so going inside, you can look at the contrast enhancement, and again, huge motion. Right, and so this is DC. And remember the navigator I've shown earlier. Here's the high resolution reconstruction of it. As you can see, we're able to reconstruct or see a lot of the transient dynamics here. Now, granted, there's still more improvement we can do to deal with the noise and so on, but this is already, we're already able to see a lot of the dynamics here. And so in summary, we've shown a method that allows us to go from 2 gigabytes K-space to a 100 gigabyte image without gating. And there's two innovations. One is a streaming reconstruction and a multi-scale low-rank representation. Thank you.